right? Because I take the same unit vector dotted with itself, no surprise. I take the derivative on both sides. Or I increment it on both sides. What is d of 1 is 0 because 1 cannot be incremented, right? It's 1. But this guy here is the following. So now I have d, and I'm going to use the product rule. You can use that for dot products as well. So this is going to be d er dotted with er, and then er dotted with d. Okay, so this says that this is equal to 0. Am I making sense to everybody? I start off with this guy. This is common sense. You know this from statics. I increment it on both sides. Or if you want to think of it as taking a time derivative on both sides. Time derivative of 1 is 0. Time derivative of these two quantities, I'm just using the product rule. But if you know dot products, they are commutative, which means A dot B is the same as B dot A. So this essentially says that 2 times makes sense to everybody? And if the dot product of 2 vectors is 0, what does it mean? They are perpendicular to each other. So DER by the same token, d E theta is perpendicular to E theta. So what do you think the direction of DER is? This guy has to be perpendicular to this one, not this one. Okay, this is the second one in the triangle. It has to be perpendicular to the original unit vector that I started off with. What's the vector perpendicular to ER and on the same plane as ER? It is going to be E theta. So the directionality of DER is actually E theta. Okay, so this means magnitude of vector DER is Z theta, E theta, exclamation mark is not needed. Likewise, what's the direction of DE theta, anybody? Negative. Because you see it's pointing in the opposite sense of D. Okay, so d theta is minus d theta e theta. But this is kind of ridiculous to keep remembering, right? So we want to come up with a generalized way of looking at it. So first of all, I have my velocity vector L by 2. This one. I'm going to get rid of this here. And 10 more minutes and then we'll stop. Might not get to solving the equation of motion. Oh, yes, question.
So this was dr and er, right?
Oh, ER, I'm sorry, yes. Yes. Not ER. Thank you. Thank you. So how to generalize this? This is the way you want to look at it. All said and done, dER by dt is magnitude by dt. Magnitude of dER is d theta. D theta by dt is theta dot. Okay, so we're going to call it as theta dot. Which is now theta dot E theta. Remember the triad. ER E theta. You don't need to write it, you already have it. Remember the rigid body. My first question to you, can I write E theta in terms of EZ and ER? I can, right? Because ER, E theta cross product gives me EZ. So if I take the cross product of EZ and ER, that gives me E theta. Okay, so this is theta dot ER, sorry. So hang on. So now I have dER by dt as, take this theta dot, I can attach it to either this EZ or ER, right? It's a scalar. Theta dot is a scalar here. It's a time variable, but the scalar. So this is theta dot EZ crossed with ER. My question to you is, what is this quantity called? If you want, I can draw the directions here. So this is the center of mass. This is ER. Theta. Into the page. What do you think is this quantity here? Not zero. It's not zero. It's not zero. It's a physical quantity. Yes.
Is it going to be a constant?
No, it's something that changes as a function of time. Yes?
Is it angular?
Angular velocity of the body. That's it. It is just omega. Where omega is the angular velocity of this rigid bar at this, on this problem. Okay, so omega. Which tells you two fundamental things or foundational things. The first thing is that the angular velocity of the body is the angular velocity of the frame attached to the body, because it's a rigid body. You cannot distinguish one from the other. So if I have a frame attached to a body, a rotating frame attached to a rotating body, the angular velocity of the body is the same as the angular velocity of the frame of reference. Okay, so that's something I'll write down here. Last few minutes. Angular velocity of the body is the angular velocity of the rotating frame. I'm going to call it as omega, vector omega for both the cases. And the second thing, it's omega cross ER, dER by dt, we just proved it. If I do dE theta by dt, I'll end up getting the following. You can try it out, you will end up getting this. Okay, it's easy to prove. which tells me, and if I do dEz by dt, omega cross Ez, so what's that? 0. It's a planar problem, so Ez is always out of the plane of the ball, or into the plane of the ball. So this tells me a fundamental truth. If I have a rigid body doing planar motion, the third unit vector does not play a role in the problem in some sense. But it also tells me something more deeper. If I have a triad of unit vectors, that's the thing that I want to write down and close off for the day. If I have a generic triad, let me call it as E1, E2, and E3, some generic triad, the rate of change of any unit vector of this triad, where I could be 1, 2, or 3, is nothing but the angular velocity of the triad crossed with the unit vector EI. If you understand this particular concept, there is no need to remember any formula in dynamics. Everything can be derived from scratch. Okay, so I'm going to stop here, but I want to see if there are any questions. I have a couple more minutes left. What I will do in the next class is I'll start off from this point, go ahead to our problem, do the velocity analysis, do the acceleration analysis, obtain the equation of motion, and then we will start looking at more complex rotational motion, right, using the Frenet-Serre frames. Okay, so this is the general flavor of this course from now on. You see that it's a lot of math, but it's math attached to certain physics, and the combination of these two gives us engineering with some approximations. Okay? So if you have questions, I'm happy to answer them. If not, thank you for coming. Have a good day. Switch off the recording.